class, welcome back. So we are on to T-Test this week. This week I'm going to be teaching you a lot of stuff conceptually. We're going to be going over all the types of T-Tests this week. We're going to be doing very minor calculations, and we're going to be focusing really what a T-Test is, what are the assumptions, when would we use it. And so let's get started. I went ahead and gave you an overview of how you might want to go about approaching learning the materials independently this week. Again, it's totally up to you, but this is just a suggested guideline. When we go through and talk about T-tests, I have that picture of a cup with 2 cups of tea. We're going to see all T-tests are, you're taking a categorical variable or a nominal variable, and you're comparing. And you're comparing for an outcome variable. And so what T-test you run is going to be determined by the type of study design you have for what you're doing. With this T-test, we still have to follow a normal distribution assumption, so that nice bell curve is something that we're still looking for. With all the T-tests that we use, our outcome variable needs to be a continuous variable. So you should remember and review what is. When we're thinking about these, again, there's 3 different T-tests. Chapter 7 discusses the single sample T-test and the related or dependent or paired T-test. Those are all 3 different names for the same T-test. And then in Chapter 8, we talk about the independent T-test. The single sample T-test is one sample compared to a population. It's used when we're interested in, oftentimes with industry. I'm interested in comparing a production line. I want to know if my batch of ketchup I just produced has the appropriate level of ounces in the bottle. So I would pull a batch, that would be my sample, and I would compare it to that known population standard ounces, the ounces you see on the label. That would be an independent sample T-test. I'm going to be focusing this week on our 2 sample T-tests, or the times where we measure things twice with this, and that's that T for 2. So in Chapter 7, you have a related or dependent or paired T-test. For that, you use a within subject design or repeated measures design. What I mean by that is that each individual gets measured 2 times. Again, that idea of T for 2. This is often used in a pre-post design or before-after design, or I get a baseline and then I get your measurements after you've taken the drug or the intervention or participated in the experiment. And then you have an independent design. And an independent T-test design is between subjects, and so one person can only be in one of those 2 conditions. So you've got 2 separate groups, 2 different groups, right? And we're going to talk more about those distinctions. I'm going to give you some basic examples here, again with the 1 sample T-test covered in Chapter 7. I could be making hot tubs. I need to make sure every hot tub takes approximately 3 minutes to heat up to 100 degrees. And so I've got this known amount of time that it's supposed to heat up to 100 degrees. I'm going to then pull off some recent hot tubs that were manufactured, making sure that they fit to that criteria. Again, a lot of production line and industry uses the single sample T-test. Chapter 7 also talks about the related samples, paired or dependent T-test. Again, those are all the same thing. We just have 3 different names for them. So here, maybe I'm doing some drug trial testing with the rats, and I want to get how active they were, and then I want them on the drug, and then I want to compare their activity level after the drug. Again, I'm testing that rat 2 times, before the drug, after the drug, pre, post. That's the related sample T-test. My independent sample T-test, which is Chapter 8, again, is a between subject T-test. I have 2 different groups. So in this example, I'm looking at the impact of preschool. So I've got some kids who went to preschool, some kids who didn't. I'm now going to look at their SAT scores and see if I see differences. So that's the independent T-test, and that's Chapter 8. Some things that we should know, again, besides you need a normal distribution with any of these T-tests, some other things that are basic that are going to apply to all the T-tests we use is you can still do directional and non-directional hypothesis testing. Remember, non-directional goes with the 2 critical values. Directional goes with the 1 critical value. With the one critical value, I have a specific direction I'm interested. Are there increases in happiness or decreases in stress or decreases in depression? Again, I can still have an idea of where I'm going to expect the outcome to be, but I can still use a non-directional research hypothesis. In that case, I'm kind of covering my bases. I'm being more conservative. In that case, I'd be able to identify if, although I expected increases in happiness, there were decreases in happiness, or if I expect decreases in stress, well, actually there were increases in stress. Again, same things apply for hypothesis testing. We still have a null, we still have a research. You still can do a non-directional test or a directional test. We will take the non-directional route moving forward because that is the most common and that is the most conservative approach. The other thing that we should know, when we tested and learned about hypothesis testing with our z-test, we had straight set critical values. That is not the case with t. T, the critical value, although I'm not going to make you look it up, is still going to be based from sample size, or actually your degrees of freedom. And so sample size does connect with degrees of freedom. So in general, the larger your sample size, the more likely it's going to correspond to that population. It's going to be a better representation of the population. You'll also see when you have a larger sample size, there's smaller critical values. A smaller critical value is going to be easier for us to reject the null. You're also going to see larger sample size give us more power. Remember, power is that ability to detect significance. So sample size is going to be an important consideration. I'm going to have us go ahead and move on to our independent t-test, Chapter 8 first. So we're going to move on to Chapter 8 first. Chapter 8 is the independent t-test that's based on a between subject design. In this case, I'm going to have 2 cups of tea. Again, T for 2. I will get a cup and you will get a cup. Again, one person can only be in each condition or each group. That is the focus of the independent t-test. With the independent t-test, again, I'm going to have the same outcome, and I'm going to be comparing that outcome between those 2 groups. Oftentimes when we use a t-test or that independent t-test between subject design, there's naturally occurring comparisons we can do. So think about where we already see 2 group differences within the world. One example could be gender. I could be interested in gender differences. Gender differences would fit into this criteria. I have a group of males, I have a group of females. Pet owners or not pet owners. Again, you're divided into those 2 different groups. If I work or if I don't work, if I'm a student or if I'm not, if I have kids or if I don't. Again, there's a lot of naturally occurring comparisons where we have just 2 groups. We can make this comparison and use the independent t-test. Again, the other conditions for this is we need a normal distribution in our data. We also need data as our outcome data. All right, so I'm going to have you think about what are ways we naturally divide people. All right, I gave you some examples, but you can come up with some more. You can also use independent t-tests if you have 2 different conditions within your experiment. So if I have a control group and I have an experimental group, I have a control group and a group that got the intervention. I had a control group and a group that got the drug. Again, those 2 different groupings would fit into this independent t-test. Another thing that we need to be concerned about with our independent t-tests, because we have 2 groups, these 2 groups are going to have their own way of responding to different things. And again, when you take research methods, you can learn more about random assignment, but we need to make sure that these 2 groups don't vary too much. So when we talk about variation or dispersion, we're talking about variance. And variance, again, is that familial relationship to standard deviation. So one thing that I'm going to have to check for is equality of variance. Another thing I should note that's on the slides, degrees of freedom for independent t-tests is going to be different than the dependent related or paired t-tests. In an independent t-test, it's going to be n minus 1 plus n minus 1. So n for the group of males and for the group of females. You could also think about that as everyone in your study minus 2, because again, we're doing minus 2 because we have 2 different groups of people. Again, those different groups of people can have different sample sizes. So when we get into this quality of variance, what I mean is I don't want, when I look at the standard deviation of males and I look at the standard deviation of females, let's say I'm interested in differences of stress, I don't want to see the variance or the standard deviation of males being really different from the variance or standard deviation of females, right? If they're too different, that violates this assumption and I can't run the independent t-test. A quick and dirty rule to look at this is if I looked at the standard deviation of males and the standard deviation of females, if they're one is 3 times greater than the other, that's bad news. So let's say the standard deviation for males with stress was 3. Let's say the variation of stress for females was 15. SD, standard deviation 15. Whoa, that's 5 times the difference of the males. I could not run an independent t-test. So again, when I look at that, we've learned about standard deviation before. Now we're looking at standard deviation between those two groups. I need to make sure my standard deviation in group 1 and my standard deviation in group 2 are similar, ideally small, because small is better for us. We want less individual differences within that group, but they could also both be large. That would be messier for my data, but that would be okay because they're similarly large. All right. Some things to consider. This is the formula. The formula for T is the differences between the two groups over estimated standard error. So I'm going to talk for a minute what estimated standard error is in a minute, but you see M1 is your mean for group 1. M2 is your mean for group 2. Again, you could do M2 minus M1 or M1 minus M2. You're just looking at those group differences between those two groups. Then you're dividing for and adjusting for differences that are happening within those groups. And we call that estimated standard error, estimated standard error for our mean differences. So I'm going to talk a little bit about that. When we look at estimated standard error for mean differences, I'm not having you calculate this, but you would get this by calculating pooled variance. And actually, I do have a homework assignment where you are given degrees of freedom and you are given the standard deviation. So you know standard deviation times standard deviation is variance, and you are going to use that pooled variance formula. This first one up here, this one right here, you're going to use this one in your homework set, and then you're going to take that number you get and you're going to put it into this formula right here. So I am going to give you a little bit of a challenge calculation problem, and then you're going to take that number, and that number is the bottom of your T, and then you would also look at the mean differences that are provided, and we're going to get through that in an example in a minute. So again, the bottom is called estimated standard error. Basically, it's trying to get at what these are samples I'm taking. It's not a population, and I'm going to be adjusting for that. And so to adjust for that, I'm going to take into account the variance that's happening as well as my sample size. This is kind of similar to what we did when we calculated the denominator or the bottom of the z-test, where you had to take sigma over n and square, or the square root of the sigma squared, which is variance of sigma over n. All right, so very kind of similar, but now it's different because we're using a different test statistic. All right, so once we get that t, then we would know, based on looking at output, if it was significant or not. We're going to get to that in just a minute. After we've made a decision, is my t significant? So is it larger than that critical value? And if it's larger than the critical value, it means it's significant. If it's significant, it means that I've rejected the null. If I got it within that center area of the distribution, when we look at a normal distribution with t, that center point is going to be t equals 0. They're saying there's no group differences. And then you're going to have negative sides of the t and positive sides of the t, just like we did with C. After I've done that, I've made a decision, reject the null, fail to reject the null. I then do my next step, which is effect size. Effect size, you can do Cohen's d. And I showed you the formula here for Cohen's d. Or another option is looking at r squared. For your homework, you will be seeing Cohen's d, and you would see the value. You don't have to calculate it. You would just be sharing what it is, and then sharing, is it small, medium, or large. If you have a d that's less than 0.2, you would say there's no effect. All right, so I don't have that on the slide, but a d less than 0.2 means there's no effect. Okay, so I'm wrapping up the first part of our t-test lecture now, and then our next part is going to go over the example with Facebook that connects to your homework.